7.1a wants us to rewrite exponents to radicals. This right here is a rational exponent. It just means it's a fractional exponent. And be careful, it doesn't mean cubed, it means cubed root. So what that means as a radical means it's going to be the cube root of 1,000. Whenever the root is higher than a square root, you have to use a little number here and show which type of root it is. Now for the second one, it's 121 to the 1/2 power. The 1/2 power just means the square root. Now for the square root, we don't actually put a little number of 2 in there. It's already implied that it's there. 7.1b wants us to rewrite radicals to exponents. This right here is the cube root of 3x to the 6th power. So what we would do is we would write it as 3x to the 6th power and do the cube root. Now here you have to be careful because one thing we know is property of exponents, this 1/3 power can be distributed to both. So we do want to actually do that and simplify. This would be 3 to the 1/3. This would be x to the 6th times 1/3. Now 6 times 1/3, what you can do is put 6 over 1, and all you do is multiply straight across. This would be 6 divided by 3, which becomes the number 2. So the final answer here is going to be 3 to the 1/3, and then it's x squared, and that's considered simplified into exponents. The next one here is the 5th root of 32 times x to the 15th. So we are just going to rewrite that as 32 x to the 15th power, and we're going to put over here to the 1/5 exponent. Again, everything in parentheses gets that exponent, so what we're going to have is 32 to the 1/5 power, x to the 15th times 1/5. Don't forget, 15 over 1 is going to go as a fraction. Multiply straight across. It'll be 15 divided by 5. 15 divided by 5 is 3. So this becomes x cubed. Now be careful, this is 32 to the 1/5 power. Is there a number that you multiply by itself 5 times that gives you 32? There actually is. It's the number 2. So this simplifies even further to 2. So our final answer here is 2x cubed. 7.1c has us evaluate nth roots without a calculator. So similar to what we just did up here. So let's continue on. This means the cube root of 1,000. It just means what number by itself 3 times equals 1,000. The answer here would be 10. So the answer to this problem is 10. This one right here is the 1/2 root of 121. If you want, you can always rewrite them as radicals. It's the square root of 121. Square root just means what number 2 times gives us 121. The answer to that would be 11, so it's 11. Now this next one here, we have 2 things going on. We have a 2 at the top of the fraction and a 3 at the bottom. In this case, what I would do is take the fraction, which is 2/3, and you're going to want to break it into 2 pieces. You're going to take a squared, and then you're going to do a 1/3. Now you get to pick and choose how you want these 2 numbers to impact 27. Do you want to square it first or take the 1/3 root? Sometimes it's easier to do the root versus the squaring. So what I'm going to do is write it as 27, and let's do 1/3 first, and then we'll come in and square it. Again, I could have chosen to square it first and then do 1/3. This just says, what's the 1/3 root of 27? Again, that just means what number 3 times by itself gets us 27. The answer with that would be a 3. So this simplifies to being 3 squared. Now we know 3 squared just means 3 times 3. The answer here is going to simplify to 9. The fourth one here, it's 32 to the negative 1/5 power root. Now we don't want negative exponents, so it's nice to get rid of those first. Any number can be written as a fraction by putting it over 1. When you move a number across the fraction bar, it changes the sign. So on the bottom of our fraction, we're going to have 32 to the 1/5 power. Now notice there's nothing on the top, so don't put 0. There's really a 1 up there. Something's just floating around, so write the 1. Now can we evaluate it? Do we know the 5th root of 32? Again, it just means what number 5 times gives me 32. That answer is 2. So this simplifies to 1/2 as our final answer. 7.1d wants us to solve equations using the nth roots. So here we have x squared is equal to 169. They want us to get x by itself. Now there's two ways we could do this one. What we're used to doing when we have squares is coming in and just taking the square root. So what we would typically do is come in and say, I'm going to take the square root, take the square root. So you would get on this one, x is equal to, be careful, it's plus or minus 13. Now that's the radical. If you want to use the exponents, you can also do that. So let me show you another way to do this. X squared equals 169. To get rid of the little 2 exponent, you can just multiply by its reciprocal, which is 1/2. If you do it to one side, you do it to the other. So what you end up getting is x is equal to 169 to the 1/2 power. Well, 169 to the 1/2 power is the exact same thing as the square root of 169. When you solve that, you are going to get the exact same answer as x equals plus or minus 13. Don't forget the plus or minus, because I can put a positive 13 in here and square it, and I can put a negative 13 in here and square it, and still get 169. The next one here is 4x to the 4th equals 324. We need to get x by itself, so we have to move the big 4 and the little exponent 4. Always leave the variable and the exponent till last. So let's get rid of the big 4. This just says 4 times. To get rid of multiplication, we're just going to divide. So we're going to end up with x to the 4th equals 81. Now to get rid of the little 4 up here, multiply by its reciprocal of 1/4. So the question is, x equals 81 to the 1/4 power. Now if you want, you can rewrite that as a radical. It just means the 4th root of 81. So what they want to know is there a number I multiply by itself 4 times that gets me 81? Sure, the number 3 is going to work. So here the answer is x equals 3. Now you want to go back and decide, can this have plus or minus? We're used to it with x squared, but what about x to the 4th? If I put a positive 3 in here and do it 4 times, I'm going to get 81. What if I put a negative 3 in here and multiply it 4 times? Negative 3 4 times is still a positive 81. So this one here does have a plus or minus. I will tell you the trick is, if the exponent is an even power, you have to have a plus and minus. If the exponent's an odd power, like these next two, there's only going to be one unique answer. So let's look at this next one. Here it's x plus 5 all cubed equals 27. Now be careful, we need to get the x by itself. Remember, you're going to work your way toward the x. So in this case, we don't do the exponent last. Because this little exponent is furthest away from the x, because the 5 is closer, we have to get rid of the little 3 first. The way to get rid of the little 3 is to multiply by its reciprocal, which in this case again is going to be 1/3. So we do 1/3. So it's x plus 5, and we can evaluate this. 27 to the 1/3 power, again, means what number? 3 times gives me 27. The answer here is 3. Now we can wrap this up. To get plus 5 by itself, we're just going to minus the 5. When you subtract 5, you're going to get the answer is equal to x is negative 2. So if we put negative 2 back into here, negative 2 plus 5 is 3. 3 cubed is 27. Again, be careful, it's not plus or minus. You'll get a completely different answer if you do plus 2. It's because the power is odd. There's only one unique answer. The next one here is similar. We have to get x minus 10 to the 5th power equals 32. To get x by itself, we have to move the minus 10 in the 5 exponent. Work your way toward the x variable. The 5 is the furthest out, so come on in and get rid of the little 5 by doing the 5th root. Now we're left with x minus 10 equals 32 to the 5th power. Again, what number 5 times is going to give us 32? Well, that answer here is 2, so that becomes a 2. To get minus 10 out of there, we're going to add 10 to both sides. Now we're going to be left with that x equals 12, and that's our final answer. 7.2a is use properties of radicals and exponents to simplify expressions. This works just like Chapter 6 did with simplifying exponents, except we have fractional exponents this time. So try to remember those properties. First thing we want to do here is we have 27 m to the 9th, n to the 15th, all to the 1/3 power. Now I can't write this 1/3 of a time, so we can't use the expansion method. We have to use our tricks. So what we need to do is distribute that 1/3 to all three pieces. So what we're going to get is it's 27 to the 1/3 power, m to the 9th times a 1/3, and n to the 15th times a 1/3. Again, any whole number can be made a fraction by putting it over 1. Let's start here with 27 to the 1/3 power. What number 3 times is 27? It's 3. This exponent here, we're going to multiply across 9 divided by 3. 9 divided by 3 becomes 3, so this is going to be m cubed. This is going to be 15 divided by 3. 15 divided by 3 is 5. This becomes n to the 5th. This answer is simplified because there's one constant value here, one m and one n, and I know I'm done. The next one here is similar. Everything in these parentheses has to be repeated 1/5 of the time. We can't logically do that, so we must use the properties of distributing this exponent. So when we do that, we're going to get 64 to the 1/5 power, r to the 10th times 1/5, s to the 5th times 1/5. Again, I'm going to come in and make all of my whole exponents a little fraction and go backwards. This is s, and this is 5 over 5, which is 1. So this just simplifies to s to the 1st power, or s. For r, it's going to be 10 over 5, which is 2. So this becomes r squared. Now for 64, is there a number 5 times that gives me 64? There actually is not. And for our Algebra 2 purposes, we're just going to keep this as 64 to the 1/5 power. Now, I will tell you in Algebra 2x, they would actually simplify this further by trying to pull out other perfect fifth roots. We're going to keep it like that for now, and we're going to call this our final answer for Algebra 2 class. This next problem here is actually just like Chapter 6. There are no fractional exponents, so it's a really good review for that. So let's go ahead and notice this is not simplified. There's 2 b's and there's 2 a's. They have to be condensed down to 1. Let's just keep the 7 there though. So the 7 is still there. For the a's, what I'm going to do is subtract the exponents. It's 3 minus 1, which is 2. So it's a squared. This is a b, which is 3 minus 2, which is going to be b to the 1st. What happens is there's nothing on the bottom, so it's just a 1. And I'm going to reverse out this 1 on the bottom and make it not a fraction anymore. So it's 7a squared b is our final answer. You also could have just done expansion on this, where you would cross off this 1a and cross 1 off here and get 2, cross off these 2 b's, cross 1 off there and get 1. So this would work. Now the last one we have, it's all fractional exponents. So let's use this similar property we did here, but with the fractions. Now I can tell that there's 2 numbers, so those must be simplified. There's 2 x's and there's 2 y's. So let's combine those. Let's start with actually the numbers first. What we have here is 5 divided by 35. So just look at that. What I can do is take 5 divided by 5 and 1. 35 divided by 5 is 7. So that's going to be 1/7 for the numbers. Now for the x's, I'm just going to subtract the top fraction minus the bottom. When you do that, you always put it on the top at first. So we're going to do 5/4 minus 2/3. And we'll come back and do that. For the y's, I'm going to do the same thing. It's y, it's 5/4 minus 3/4. And again, you always start with it on the top. So it's 5/4 minus 3/4. Now this one's easy to simplify because the common denominator is already there. 5 minus 3 is 2, and it would be 2 over 4. If we simplify that, 2 over 4 becomes the number 1/2. So let's just rewrite that as 1. We'll keep the 7, and let's just do y to the 1/2 right now, and that's cleaned up. Let's deal with this x. The x here needs to have a common denominator before we can subtract the fractions. A common denominator between 4 and 3 would be 12. So let's go ahead and multiply this side by 3 and this one by 4. What that's going to look like then is 15 over 12. And then over here you're going to have 8 over 12. So when you write that, you have 8 over 12. Now you can subtract that. 15 minus 8 is 7 over 12. So for the x variable, let's come back up here and do 7x and do 7 over 12. So our final answer, once it's cleaned up, is x to the 7/12, y to the 1/2, all over 7, and that's simplified. 7.2b, add or subtract like radicals. This is actually very easy to do, even though it looks complicated. Just remember, if I were to ask you to add 2x plus 3x, you'd add it together and say it was 5x. All you're doing is you're matching these variables, and then you just add the numbers. So when you look at this first problem here, you're going to notice that the square root of 3 and the square root of 3 match. So all you have to do is do 4 plus 6, which is 10. So add that, that's 10, and then you're just going to put the cube root of x. And that's all you have to do. So this next one here, it's a 7ab to the 4/5 minus 16ab to the 4/5. ab to the 4/5 match up, so those two are like terms. So all you have to do is do 7 minus 16. 7 minus 16 is a negative 9, and then you just put ab to the 4/5. And that's our final answer. 7.3 A and C, we're going to solve radical equations and check for extraneous solutions. Solutions that are extraneous are answers that you get that when you plug it back into the equation actually doesn't work. As we deal with more advanced types of equations, extraneous solutions can happen, so you must check for them. So let's get started with this first one. Here we have the cube root of x minus 3 equals 6. Now you can either keep it as a radical symbol, or if you want, you can rewrite this as a rational exponent. Remember, the cube root is just the exponent, 1/3. So if I do that, we have 1/3 equals 6. Now we've already solved for one like this before. X is here, and we have to get rid of the minus 3 and the 1/3. Start your way furthest out. 1/3 is the furthest out. To get rid of 1/3, you're going to cube it, or 3 over 1 as the reciprocal. Now to simplify this, what you're going to get is x minus 3. And if you do 6 cubed in your calculator, you're going to get 216. Now all you have to do is add 3 to both sides to finish. And your final answer here is x equals 219. So now you do want to check this and see if it works. If you put 219 in for x, 219 minus 3 would be 216. The cube root of 216 would be 6, so it's fine, and we did double check that the solution is not extraneous. The next one here, we have 2 square roots on both sides. Now what I could do again is I can rewrite them, so if they're written as rational exponents, you might like that better. You don't have to, but it's the 1/2 power. And this is 3x plus 4 to the 1/2 power. Now notice, to solve for x here on either side, they're locked in with this 1/2 power at the end. They're both furthest out from the x, so get rid of that first. To get rid of the 1/2 power, all you would do is multiply by its reciprocal of 2 over 1. When you do that, what happens is you're going to notice the exponents clear out. So then you're just left with x minus 8 equals 3x plus 4. Now we just have to go ahead and solve this equation. I'm going to bring 3x over to this side, so I'm going to subtract 3x from both sides. When we do that, we get negative 2x minus 8 equals 4. Now I have to move the 8 by adding 8 to both sides. That's going to leave me with negative 2x equals 12. Wrap this up by dividing both sides by the negative 2. When you do it with a negative 2, be careful, you're going to get negative 6 as your answer. Let's make sure it's not extraneous. If I put negative 6 into here, what I would get is negative 6 minus 8 is negative 14. So I'm going to write that up here. It's negative 14. Then if we put the negative 6 into here, 3 times negative 6 is negative 18 plus 4 is negative 14. Now it's going to be negative 14. Now here you need to be careful. Yes, these two sides do equal. However, we're only dealing with real number answers in this chapter. The square root of negative 14 is not a real number answer. It's actually imaginary. So in this case, this is not a valid solution because we get an imaginary answer. So I'm going to cross it off, and this one we say is considered to be extraneous. That is, it's a false solution because it gave us an imaginary answer when, again, we're only dealing with real numbers in this chapter. The last one here, before we solve it, we have the square root of 5x minus 4 minus the square root of 3 equals 0. The easiest way to solve this is to make it look like this one. So keep this square root on this side and move this one over to that side. To move this square root, what we have to do is we're going to add the square root of 3x to both sides. And as I do that, I'm going to actually change it to be 5x minus 4 to the 1/2 power. I'm going to rewrite it as an exponent. And then over here, it's going to be 3x to the 1/2 power. Now again, the thing furthest out from both of these x's is the 1/2 power. So let's get rid of that first by multiplying by its reciprocal of 2 over 1, which means the exponents cancel out. Now we're left with 5x minus 4 equals 3x. I'm going to take the 5x over here and move it to this side. So let's subtract 5x from both sides. That's going to leave us with negative 4 equals negative 2x. We're going to divide by the negative 2 on both sides. And that gives us a final answer that x equals 2. Now, let's try x equals 2 back into here. 5 times 2 is 10 minus 4 is the square root of 6. If I put 2 into here, 3 times 2 is 6, so it's the square root of 6 equals 0. This here is a true statement, and the square root of a positive 6 is perfectly fine. So this is a valid answer. It's not extraneous. We're going to keep the answer as 2. 7.3 B and C is solve equations with rational exponents, and then check again for extraneous. Now, this is similar here to what we just did. There are no radicals, there are already rational exponents. Again, to get x by itself, we're going to work our way closest or furthest from the x. So we have to get rid of the minus 2 first, so let's add 2 to both sides. When you add 2, we're going to get x minus 3 to the 2/5 power equals 4. The next thing to get rid of is the 2/5 power, so multiply by its reciprocal of 5/2. That's going to leave us with x minus 3 equals 4 to the 5/2. Now we do want to go ahead and simplify 4 to the 5/2. Remember, we can take 5/2 and split it into 2. So what I can do is either do 4 to the 5, then do the 1/2 power, or I can do 4 to the 1/2 power, and then the 5th power. It's easier for me to take 4 to the 1/2 power. 4 to the 1/2 power is the square root of 4. The square root of 4 is 2. And then I have to keep the 5 there. 2 to the 5th power is 32. So this number right here is the number 32. So let's change it to x minus 3 equals 32. Let's wrap up the problem by adding 3 to both sides, which would give us an x of being 35. Now let's double check it, see if it's extraneous or not. If I put 35 in here, 35 minus 3 is 32. So it would be 32 to the 2/5 power. 32 to the 2/5 power is going to be the number 4. 4 minus 2 is going to give me 2. This is a perfectly fine answer, and it's not extraneous. 7.4 A and E wants us to add and subtract functions and then state domains of the function. So here we have the f of x is 4x minus 7, g of x is 3x plus 2. They want us to find h of x and state its domain. Here h of x, they want us to take f of x plus g of x. So all we have to do is find f of x, which is 4x minus 7, and put it in there. Find g of x, which is 3x plus 2, and put it in there. So let's go ahead and do that. And they're going to call it h of x. It's just a label. So 4x minus 7, and then it's going to be plus 3x plus 2. All we have to do here is add the like terms together. So 4x plus 3x is 7x. Negative 7 plus a positive 2 is negative 5. This is our final answer. Now the domain means what can the x value be? If you look at the x value here, they're saying, is there any number that you cannot put in for x because it won't calculate it? I can put in the number 0, I can put a negative number, I can put a whole number, I can put a fraction, I can put a decimal, I can put a square root. Any type of number will work. Here the domain, what we're going to say is all real numbers, meaning there's nothing that will not work in here. Every single x value is possible. Let's go on to the next one. H of x is f of x minus g of x. So when we write that, what we're going to have is we're going to have h of x. Now f of x is 4x minus 7. G of x is 3x plus 2, but it's minus. Now you have to be careful on this one. This negative has to be distributed to both, so that's the only tricky piece. So let's distribute that to both and see what we get. So that means h of x is equal to 4x minus 7 minus 3x minus 2. When you add your like terms, it's 4x minus 3x, which is 1x. Negative 7 minus 2 is negative 9. So our final answer here is 1x minus 9. Now the domain on here again, is there any value of x that won't work? This is a linear function. Everything works for this one. So I'm going to do this shorthand. The domain, what you can do is write is, this capital R with a slash means all real numbers. So this symbol here is the same as writing all real numbers. The last one is g of x minus f of x, so let's write that one out. So here h of x is our g of x, which is 3x plus 2. This time we reverse the order. We minus 4x minus 7. Again, just don't forget to come on in and make sure you distribute that negative sign to both of these pieces. When you rewrite it, it's going to look like this. H of x equals 3x plus 2 minus 4x plus 7. Add your like terms together. 3x minus 4x is negative 1x. Plus 2 plus 7 is 9. So our answer here is h of x equals negative 1x plus 9. The domain in this case, again, I can put any value in for x and it works. So I'm going to put the domain is all real numbers. 7.4, B, C, and E want us to multiply functions, divide functions, and then state the domain of the function. So here we have f of x is 2x to the 4th, g of x is 6x. Let's find h of x again. Here h of x is the f function, which is this, times the g function, which is this. So let's just replace that. H of x is equal to, f is 2x to the 4th, and the g function is 6x. Now all we do here is multiply like terms together. So 2 times 6 is 12. And here we have x to the 4th, x to the 1st, those combine to x to the 5th. That's our h function. Now the domain on this, again, is there any value of x that will not work? And on here, the domain is going to be all real numbers. I can put any type of number in for x, and I'll get an answer. This next one here, h of x, is g of x divided by f of x. So g of x is 6x, f of x is 2x to the 4th. Now I can simplify this, be careful. Two numbers need to be simplified. 6 divided by 2 is 3. And what I can do here, this x can be crossed off, and then I'm left with 3 down here, so it's x cubed. This here is our final answer. Now the domain for here, this one actually does have a little bit of a twist to it. When you have a fraction, there's a certain number that can never be on the bottom of the fraction, and that's the number 0. So I can put any number in here and it's okay, but if I put the number 0, it's not going to work. So the domain is all real numbers, is what I'm going to say, except 0. 7.4d wants us to evaluate function composition. So here we have f of x is 2x plus 3, g of x is 3x squared. They want us to first find f of g of x. After we do that, let's evaluate it when x is 3. So remember, there's two ways to think about this. First thing you can do to find f of g of x is you can substitute g of x into here. G of x is 3x squared, so I'm going to actually put that in there. So I'm going to do f of 3x squared. Now what the question is here, it says go to the f function, which is right here. Wherever you see x, put 3x squared. So what I'm going to do is put that there. So when I rewrite it, again remember it says rewrite the f function, which is 2x plus 3. So it's 2, used to be an x plus 3. They don't want the x there, they want 3x squared in its place, so that goes right there. Simplify this, you get 6x squared plus 3, and that's your final answer. Now you can think of this a different way if you're struggling with that approach. It's actually a little bit of a shortcut. Here's what it says. Take the g of x function and put it into f. So if you take g of x and plug it into f, here's what you would do. You would imagine taking the g of x function and plugging it in to an x there. If you do that, you can jump right to doing 2 times 3x squared plus 3. When you simplify it, you're going to get the same answer. Now they want us to take this answer right here and see what the answer is when x is 3. So let's do that. 6, 3 squared plus 3. Don't forget your PEMDAS or order of operations. You must do 3 squared first. 3 squared is 9. So this is 6 times 9 plus 3, which is 54 plus 3, which equals 57. 7.5a, state the inverse of a relation. A relation is just a set of ordered pairs. And it says here, find the inverse of this relation. All you have to do is for an inverse is you flip-flop x and y. So for the first ordered pair of 4, 5, it becomes 5, 4. The next ordered pair flips and becomes 6, negative 3. The next one is 1, 5. And the last one becomes negative 1, 1. That's all you have to do. 7.5, D, C, and B go together. It's really D that we're doing. You can use C and B if you need to. Here it says find the inverse of an equation. And then if we want to verify two functions are inverses, we can by graphing, and we can verify through function composition. These last two methods are just good ways to check your answer to see if you're right. So here's 3 equations. Let's find the inverses of these equations. First thing to know is f of x really just means the letter y, so you can rewrite it like that. Up here for relation, all we did is we flip-flopped x and y. We made yx and xy. You do the same thing down here. So for an inverse, all you do is you take x and make it y. You take y and make it x. So this becomes x equals 2y plus 5. Now all you have to do is solve the equation for y. So we have to get rid of the 2 and the 5. The 5 is furthest away, so let's subtract 5 from both sides. Then we're going to get x minus 5 equals 2y. To get rid of the 2, divide everything by 2. When I rewrite it, I get y equals x over 2 minus 5 over 2. And that is your final answer. Now you can actually graph this to see if you're correct. The trick to the graphing is this. If you sketch out a little piece of graph paper, and then you imagine the line y equals x is right there. When you graph this equation, it's going to look something like this. So this green line here is the original graph. Now if you graph this equation, what you're going to see is this green line should flip over the line y equals x. So you can double check if you have the right answer. If you do not see the original equation and your new algebraic equation have a flip over the line y equals x, you probably have a mathematical error in here. So that's how you can check by graphing. Let's move on to the next one. Let's go ahead and change f of x to y. So it gives us 3/4 x minus 1. Let's flip-flop the x and the y to find its inverse. Now, let's solve for y. I'm going to go ahead and add 1 to both sides. Leaves with this x plus 1 equals 3/4 y. Now, to get rid of the 3/4, the easiest way to do it is to multiply by its reciprocal. But you have to do everything by the reciprocal. So this gets multiplied, and so does this. So when you rewrite this, you're going to get y equals 4/3 x plus 4/3. And that's your final answer for the inverse. Again, you can check if you have it right in your graphing calculator. Type this equation here, type this equation here, and then also add the line y equals x. When you graph all three of them, you should see some type of flipping relationship. The last one here, let's finish this up. Let's make this y equals 36x squared. Let's flip the x and the y and switch them around. Now to solve for this y, I have to get rid of the 36 and the squared. This is connected, so let's get rid of the 36 first by dividing by 36. So that leaves with the x divided by 36 equals y squared. To get rid of y squared, you can take the square root. Don't forget, this does become plus and minus. Now what you can do for this is you can write the final answer is y equals plus or minus. This becomes the square root of x. And down here it's just the square root of 36, which actually is the number 6. So you can break this up into square root of x, square root of 36, and simplify. This here is your final answer. You can graph it and you will see this type of relationship. It'll look something like this, where the original equation is this blue line graph here. The red one is this curve. You will see that the blue one is flipped over the line, y equals x, and gives you this. 7.5e wants you to determine if an inverse is a function. So use the horizontal line test to determine if an equation's inverse is a function. Remember, the definition of a function is for every x there's only one y. To decide if something's a function, you could use the vertical line test. But here's what they want us to do. Determine if the equation's inverse is a function. This is the original equation. What I would have to do is actually mathematically find the inverse and then graph it. If you don't want to do that, there's a shortcut where you never have to find the inverse. All you need to do is graph this line. If I graph this line, it's going to be something like this on graph paper. And what you do is a horizontal line test. Can you draw a horizontal line on here and it will never cross in more than one point? All horizontal lines only cross in one point, which means if I were to find the inverse of this equation and graph it, it would pass the vertical line test. By the way, we did find this inverse already, which was up here. This inverse, if I do graph it, is going to look something along the lines of this graph here. So it's more work. I could take this, do the algebra, find the equation, graph it, and say, yeah, the green line passes the vertical line test. I don't want to waste my time. I want to take the original graph and sketch it, and then test the horizontal line test. This horizontal line test tells me the green one will pass the vertical. So it's a shortcut. So the answer here is yes. If I were to find the inverse of this graph and sketch it, this would pass the vertical line test. So let's just use this shortcut on these. Let's go ahead and sketch this next one. So the y-intercept is here, and if we do a quick sketch, it looks like that. Clearly, this graph passes the horizontal line test. So yes, if I were to find this graph's inverse and sketch it, that would pass the vertical. This guy here is the parabola. When you sketch it, it's going to look something like that. Now, if you do a horizontal line test on here, clearly this one fails in many, many points, which means if I were to find this equation's inverse, which would be a sideways u, that sideways u would fail the vertical line test. So here, the answer is no. When I find this inverse, it will not be a function. 7.6a and b, graph square roots and cubic functions, state domains and ranges of those. So here we have three different equations to graph. Let's just go ahead and sketch the graph of all three of these first. So in your graphing calculator, type y equals 5 to the square root of x. When you do that, you're going to get something that looks like this. Let's sketch this one. Now this one, what you could do to type into the calculator, you can actually type y equals 2. Remember, if you wanted to, you could raise this to the 1/3 power. That's what the cube root means. There's also a button under the math functionality. When you sketch this one, here's what it looks like. It's going to have a similar shape to this right here. This last one here, you can just type it into your graphing calculator. When you do that, what it's going to end up looking like is something like this, like that. Now, let's go ahead and talk about domains and ranges. The domain, again, deals with the x's, the ranges deals with the y's. D comes before R as x comes before y, so that's how I remember that the domain means the x values. So the question is, for this particular equation, is there any number the x can't be? Here's the easiest way to do it, is look at the x-axis. This is the x-axis right here. You're going to notice over here on the x-axis where it's the negative x values, there's no green graph. The green graph does not start until the number 0, which means it couldn't find any answers until 0. Well, if you think about it logically, under a square root, we can only have numbers that are positive. So anything 0 or higher works. Again, travel along the x-axis, no activity starts until 0. So here the domain is all the x's greater than or equal to the number 0. Let's use that same approach. This next graph, here's the x-axis. If you travel along the x-axis, you actually see graph activity over here. As you're over here, there's graph. Over here, there's graph. There's nowhere on the graph that you don't see x activity. So here the domain is going to be is all real numbers. There's no number that's not going to work, and you can see it again along the x-axis. For this last one, again the x-axis. As you travel, there's no negative x's, so they're not going to work. Once you hit the x at 0, you start seeing green graph, and you see it all the way into positive x's. So here the domain is all the x's greater than or equal to 0. Now let's look at the range. So again, remember, D comes before R and X comes before Y, so the range means all the Y values. I'm going to do the same thing. Here's the Y-axis. As I travel along the Y-axis and these negative Y's, there's no green graph, so the range cannot include any negative Y's. I don't start seeing graph activity along the Y-axis until I hit 0. So here the range is all the Y's greater than or equal to 0. And again, if you look at the Y's greater than or equal to 0, you see green graph. On the second graph, here's our Y-axis. As you travel, keep in mind, as I look down here in these negative Y's, I don't technically see the graph, but this graph continues on forever. So there is graph activity in this entire picture for the Y's. So here the range is all real numbers. There's no limitation when we have a cube root. You're going to find if you have a root here and it's an odd power, like 3 or 5, your domain and range is going to be all real numbers because the similar pattern is going to show up. Now when you go to this last one here, here's our y-axis. Be a little careful. Under the negative y's, we don't see any green graph. Even at 0, we don't see green graph yet. We don't see the green graph start until the number 1. So here the range is going to be all the y's greater than or equal to positive 1. Again, just be cautious. The graph doesn't start on the y's until 1. The reason for that is the domain has to be 0 or higher. When x is 0, it's 2 times the square root of 0, which is 0, plus 1. This answer is going to be 1. That's the smallest the y's can be.